Thanks for joining us this afternoon. My name is Jamie Orlando. I am the Director of Marketing and Sales here at Butler Technologies, and I just wanted to tell you a little bit about Butler Technologies before we get started. So if you're not familiar with us, I know I've seen a lot of familiar names and faces. Butler Technologies, we are a high-tech precision printers that specialize in printed electronics and user interface products. We've been in business for over 30 years. We're currently located in Butler, Pennsylvania, which is an hour north of Pittsburgh. So we have our group here. We love to help design, develop, manufacture printed electronics and user interface products. We've got a full team of engineers in manufacturing here on site. We do everything with the printed electronics side here in the United States, just north of Pittsburgh. So we have some of our team here that's also in the webinar. I just wanted to quickly introduce our team, and then we'll get on with the presentation. So Tristan Tripodi is on the line. He is our president of Butler Technologies. You've got our business development and sales team, which is also online. On our printed electronics side, you've got Kelly Fenwick and Todd Gray. They help with any of the wearables and printed electronics. On our user interface side, you've got Steve Sweeter and Marilyn Succi. They're both on the line now, as well as Mark Bachman, who is our Director of Engineering here at Butler Tech. So what I want to do now is just quickly introduce our speaker today and then turn it over to Mike to let him present. So for those of you that don't know Mike, he is our Chief Operations Officer. Mike has a background in engineering that he got from Penn State University. For those of you, okay. It fell short. Anyway, so Mike's got a degree in engineering. He's got a background, an MBA, project management. He's got over 20 years of experience in the industry. He's been with us for over 20 years. He's also on the board of directors for the Printing United Alliance. So I just wanted to introduce Mike Wagner and let him take it from here.
Hey, thank you everybody for joining us. Good morning, good afternoon, wherever you might be. As Jamie mentioned, you can type in your questions during the presentation in the chat feature, and we'll address them as we can. If you don't get your questions in during the webinar, there will be time available at the end. So let's get started. So obviously, you see by the title slide, we're talking about wearable heater technology, and is it right for you? If you have an application you think you might want to integrate heating into, we'll discuss a little bit of basics today, and then you can always reach out after the webinar and see if somebody here can give you a hand with your application. So what are printed heaters? Printed heaters are described as one or more simple heating elements that are screen printed on thin, flexible, and sometimes stretchable materials. They utilize printed resistive heating elements rather than wires or coils, and are produced using an additive manufacturing process, unlike an etched heater or a bladed heater. What are some of the typical materials that we use for these types of wearable heaters? Most common is the thermoplastic polyurethane. So it's a very thin, flexible, and stretchable material. It's very conformable, which makes it great for fabrics and things like that that conform to the body. It's very quiet when it's flexed, and it has a hot melt adhesive backing, so you can mount it to the textile or the fabric. So that makes it all in all a great substrate for wearables. Another material that we do use is polyester, which a lot of people are familiar with heaters. We typically use very thin, maybe 3 mil, no more than 5 mil for these types of wearable heaters. And it's a little noisier when flexed. There's some things you can do to offset that. You can even apply a TPU film to one side or the other, or both sides to limit that noise a bit, or provide a decorative cover. The PET has good dimensional stability. So it's really good if you're using it for more of a really tight design, which you need to maintain print registration. And then it's really good for automotive industrial applications, but you can use it for wearable things like a back brace or certain things that are a little more rigid and don't have to really stretch.
I do have some examples here, Mike, just to show everybody.
That's right.
Just quickly, so that you can see the difference. I have here. The main thing is you don't need to see the details on this, but the main thing is to listen to the difference. So this is a heater printed on a TPU. This is, again, a thin stretchable material. So it's pliable and stretchable, and this is good for wearable applications where you're bonding it to fabric. But we also have heaters where we're, like Mike had said, we put it onto a rigid PET, and you can hear the difference in this. It's more rigid, maybe not as good for applying to fabrics, but it's good for automotive or maybe something where you have to slip it into a pocket and it needs some physical strength.
All right, let's continue on. So we want to talk about a couple of different heater types, and the first one we'll talk about is a fixed resistance heater, which is very typical. You can think of, burners on a stove where you're putting current through a coil and it heats up, gets red hot, depending on how high you have the temperature setting. And you can basically mimic those by printing coils or traces and things like that on your thin film material. So you can kind of see, if you have an industrial application, this diagram kind of shows how the temperature starts to heat up, which is the red line, and then it'll start to cool down, and then this will be your power controller, which will then kick off and kick off. Just think much like your furnace thermostat. As the house cools, it'll kick back on. So that's kind of a process that just keeps cycling depending on your area where you're heating. If it's in a area where you're losing heat very rapidly or in a systematic way, it'll kick on and off. So we talked about this a little bit briefly ago about the heating elements being a screen printed resistive carbon or a carbon blend ink, which could be a blend of silver and carbon or other things. These types of heaters typically require less or fewer print steps because we can get away with maybe using bus bar material and the heating coils out of the same ink. So it reduces the number of ink or the number of print passes that you need to achieve the design. These can be used and designed for stretchable applications, primarily on TPU. Unlike PTC heaters, there's a minimal resistance change as the temperature increases. And we'll see a little bit more information on that in subsequent slides. For fixed resistance heaters, you typically would have a closed loop or a feedback control system, much like, again, a thermostat. So you're measuring temperature and it's kicking on and off the power supply to heat that. We've done some wearables where we've mounted a surface mount thermistor. And in other applications, you could do something like a current monitoring chip, which is set for an acceptable range. And that'll really give you an idea of what temperature you're controlling just by the current that's flowing through that heater. And then for these fixed resistance heaters, again, a typical range for something like that for a wearable is roughly 68F to 122F or 20 to 50 degrees C. You can go higher even for the wearables. And most typically you're 122 to 176 or 50 to 80 degrees C for auto and industrial. But again, you can use a warmer temperature for wearables if you're trying to heat through multiple materials, such as maybe a back brace or something with some foam on it for comfort. So you may have to go up a little bit higher. You definitely don't want to have anything touch bare skin that's really hot. Anything probably greater than 115, 120 starts to burn after a few minutes. So it gets a little hot for skin. And again, one thing you can do to manage these heaters is you can lower the voltage. So you can design a heater for 1 voltage, and then if you want to turn it down or decrease the heat, you can lower the voltage. So you can control it that way too. If you put heat settings on your controller or a battery source that's custom designed, things of that nature. So temperature can decrease, the current decreases, the resistance level at the equilibrium temp decreases, and obviously the power consumption decreases. So it's just different ways you can do that. Now for these wearable fixed resistance heaters, if you use a battery pack, you really don't have that jump like we saw on the last diagram, where it's more of a slight change in the power. The resistance doesn't really change very much as it cools down. So it's a little less dramatic in that effect as far as this blue line where the power drops to 0. You're constantly feeding that with a battery. So we'll get into a little bit detail of how that works with the PTC here. So here's a animated slide of a fixed resistance heater and all of its layers. So I'll just let that play. And in that design, you'll see these coils or kind of sine wave shaped or horseshoe shaped traces. Those are the heating elements, and those are designed to allow stretch as you pull those along its x-axis. So that in itself allows for some stretch. You know, typically people are going maybe 10 to 30% stretch on some of these garments. So you definitely want to consider that when you select a heater. And we'll talk a bit about that in later slides in regards to critical design elements. Now we're going to go into PTC heaters. And again, these things do very similar things, but they operate a little bit differently. So this is, you know, these slides are going to get a little complicated or a little busy, so we'll kind of work through them slowly. And if you have questions at the end or even offline, please reach out to us and we can elaborate a little more. But the thing about a PTC heater, it has what's called PTC carbon ink. So it has special properties that allow it to change a bit as it's heating. So these PTC inks will get more resistive as the temperature of the heater increases. So you can kind of see the temperature rise is very quick and then it starts to level off. Probably around 40 seconds or so, the heater will reach its equilibrium temperature. All the while that the heater itself draws more power at startup and then goes down to an equilibrium. So your power consumption is less once it reaches its equilibrium temperature or its shutoff temperature. So by the math, I don't want to bore you too much with this, but you can see the power initial is the same input voltage and it's drawing 0.996 amps. So the power required at that point is 11.6 watts. As it reaches its equilibrium temperature, it's now drawing 465 milliamps or 0.465 amps, and now it's drawing a 5.6 watts at its equilibrium temperature. So that's what you would probably design around when you're worrying about your power source. That in itself, when you see the current changing, that's the PTC effect. The heater draws less current at its equilibrium temperature because the resistance increases as the temp rises. And we'll expand on this topic on the next slide. Heating elements in PTC heaters are made of resistive tiles or even strips, or even not recommended, but you can do one big patch of carbon ink, but it definitely has some downsides to it when you're screen printing and maintaining consistency. The ink itself, because the heater will shut off once it reaches its equilibrium or shut off temperature, is a self-limiting heater. They're not designed to be stretchable, but they're highly conformable. So they're really ideal for jackets and gloves and things that don't stretch much, like ski gloves, things of that nature. Again, these types of heaters quickly reach their desired temperature, approximately 40 seconds, and then the power drops to a steady state. So that's always good as far as how much your battery or how quickly your battery is drained if you're using a rechargeable type battery. And here's where we start talking about the resistive properties of the heater. So you can see the resistance initially when that heater is cold. Follow the math, there's a little over 12 ohms, and when it gets hot, it reaches a maximum resistance of 25, almost 26 ohms. So that's the inherent property of the ink. It actually changes resistive properties and allows it to choke off current, which then when there's less current flowing through the heater cools. So that's a kind of an iterative process. It gets slight changes up and down, but you don't notice that as a person wearing this heater. And you can get all of these information, you know, from the data sheet. So this resistive magnification factor is used in the design. I know I need to be a certain level when it's hot. I can go back and then look and see what my resistance needs to be as I'm producing this when it's cold, because you can't heat it up as you're going through the process of screen printing these. So it's a very useful tool, and you just reference the PTC inks data sheet, and they typically have this type of curve, and you can see on the curve that the resistive magnification factor changes. So here's about a 2.8 factor, and it's right in the same. So this heater is designed for about 60 C maximum temperature. Again, complicated, but we can always chat about this offline to get a better understanding. Again, similar ideas to the fixed resistance as far as temperature ranges. Again, same things happen when you lower the voltage, you can decrease the temperature. So you can set up multiple heat settings for your heater. So you can go low, medium, and high. And typically then those will last different times before the battery drains. And here's another animated video of the PTC construction. And this one, you'll see the interdigitated silver fingers in the bus bar system, and then those tiles that are actually the resistors that heat. And again, you'll see a cover layer coming up on the last slide. That can be clear. It can be decorated with a logo, a pattern, something like that, depending if you're doing some type of floral pattern. You can do all kind of neat things with that to match the garment that you're doing.
Hey, Mike, we have a question from Ron, and he asked, are PTC heaters usable in washable applications?
Yes, so these are designed typically, we found anywhere between 25 and 50 washes. So it makes sense if you're doing like a winter coat, you typically maybe wash that once a season, twice a season, depending on how you use your jacket, obviously. So you're going to get many seasons out of that jacket. Again, a heater, let's say for a garment, like a shirt where you wear it once a week, you're not going to get a long life out of that. You might get a year out of something like that. So I don't know if that answers your question, but if you have more details you'd like to follow up with, please reach out to us. So here's a video of a PTC heater heating up. So this is run about 300 times faster than normal. So it's about a 13-second video. The heater heats up in about 40 seconds. So this is a thermal imaging camera, and it takes a picture and then a thermal images and marries the two. So that's why you kind of see a little bit of an offset from the thermal image to the kind of the graphic where the border and the stars and things are. But you can kind of see the heating tiles in there heat up.
Mike, we've got another question here for you.
Yes. Yep.
So Chris asked if there are any FDA-related safety requirements such as SAR or MPE when using wearables.
The only things we've come across are, being very careful of the power supply that you're using. The customers that we deal with basically design their own, and they have to make sure that they're properly used with the heaters. And let's say if I buy a jacket that you build and you put a heating supply in there, you don't change, like I'm a user, I don't change it out and create a different voltage or something like that. And then you don't want direct contact with the skin necessarily. So you have to worry about the heat touching skin. So that's one reason why I put covers on that. And typically if you're in a jacket, for example, you have another layer of clothing on underneath your jacket, so you're not in direct contact with the skin. That's kind of the only issues we've come across right now. Most of our customers handle that on their specific applications. We basically produce the heaters, help them a little bit with the integration if they're not used to that. And then typically they'll work, or we can work with their garment manufacturers if they're not a garment manufacturer themselves, to help them integrate that into the clothing, typically through heat press settings. Trying to think if there's anything else.
Yeah, there's a second part to that question too.
Yeah.
It's, are there any unique EMI or EMC challenges?
We have not come across that. So I can't really answer that. So everything we've worked with our customers, we have not found that to be an issue. I mean, that's about as best as I can answer that.
Good, thanks.
So let's talk about some benefits of traditional or our printed heaters over traditional wired heaters. So there's increased comfort, higher flexibility, they're stretchable depending on what construction you use. They're washable. Again, you can put them in wearable designs like coats, garments, whatever. Since they're self-limiting, they're safe. They fail to cold. For example, you'll see in the picture there like a heating blanket that has wires in it. If those get kinked or nicked, they can create hot spots because the resistance goes very high in that area. And obviously you can see that caught on fire. So these printed heaters with some safety measures, operate a little more safely in those because you're also not putting, 110 and then stepping that down into the heater. So we're typically using 7 to 20 volts in something like this, DC. And then the TPU versions of these wearable heaters offer very quiet operation. Now let's talk about some market applications. If you are thinking about, you have a garment, you know your markets, but there might be other ones. If you add heat, you can go into. So medical, again, there's a back brace. So you have braces for back pain, sleeves, compression sleeves that will slide over joints for joint pain, and then different types of bandages, a KT tape. You can add heat and different things to those as well. Physical therapy, there's muscle recovery, muscle relaxation, increased range of motion. So all these different types of sleeves, braces, all those, it's kind of endless. As long as you can build something you can wear, you can add heat to this primarily and use it in these applications. And again, health and wellness, heating, blankets and bedding. Maybe hospitals want a warm blanket. Right now they stick them in a warmer and they give you a warm blanket, but it cools off pretty quickly. This is something they could, have a battery pack or plug into a source and keep you warm for hours. And then heating pads just for health and wellness purposes. And we're all familiar with heating pads. Outerwear, again, you can see by the image, there's things like coats and gloves, primarily recreational sports, right? Skiing, hiking, running, if you run in cold weather, bicycling, same thing, hunting, camping, ice fishing, snowmobile, anything you think you need to stay warm, you can add to that by adding a heater to give you a little increased benefit of heat in really extreme cold temperatures. Field work wear. So what does that mean? People that work in energy, utilities, construction, law enforcement, emergency response, airport and transit crews are something you don't often think of, but they're outside almost all day. And then special event stadium crews, same thing. They're outside for a very long time during these events. Transportation. Now this is where it gets a little crossover from wearables into more of an industrial and automotive application, but there are a few unique applications in these where they do use, let's say, fabric like seats, maybe the inside the roof of your car, the headboard, things like that. So automotive and transport. So I've kind of highlighted in orange some of the applications that could really apply to these types of wearable heaters. Seat heaters, steering wheel covers, and cabin heaters really lend themselves well to these textile-based heaters. Aerospace, again, a lot of heaters can be used in these, but again, seat heaters really lend themselves well to the fabric seats. And then construction, agriculture, potentially cabin heaters, but really seat heaters, things like that. Again, anything that might be textile related or leather related inside of a vehicle. So let's talk about some of the critical design elements of heaters. What do we need to know to help you out? What do you need to do when you start doing research for one of these things to see if it applies to your applications? One thing you want to know is the end use, right? Is it a garment that's going to be outside, inside, from like a medical type of device? Some of the considerations: does it need to flex? Does it need to stretch? Does it need to conform? Industrial or wearable? Conformable applications, heater for a winter coat. There's flex but no stretch, typically woven fabrics. Woven fabrics typically don't stretch, but they can if you use stretchable elements in that as far as the thread. And then for this, a PTC heater design is ideal. If it just needs to conform to the body, you're great. If it needs to stretch, probably not a good fit. So if you have a stretchable application, kind of like the jacket in the picture, it's a stretchable denim. Heater for a recreational type jacket, it flexes and stretches, so it's more of a knit fabric, right? Or it could be a special woven fabric that uses elastic thread. Now it's mechanically designed for flex, so you can see that horseshoe design, and you'll see at the very bottom of these, it's designed to be a little thicker. So if that does thin out as you stretch that in the horizontal position, it'll thin out and be very similar to these elements in the vertical position that don't typically thin out. Again, there's a kind of a thermal image. Things that are critical to design are temperature considerations. What temperature range do you need your heater to operate? Is it an outside or inside application? Again, outside, you may have thermal issues where the cold is pulling things away from your heater. So again, wearable heaters, 95 degrees F from a lot of our customers is typically what they want to shoot for if the heater actually touches the skin for certain applications. Very comfortable. You can tolerate higher temperatures, but you get very warm very quickly, maybe start to sweat. Not comfortable for a wear for long purposes. Up to 110 is usually safe for direct skin contact, but again, may be uncomfortable for prolonged periods. For a lot of the jacket heaters that we've built, 110 degrees F is a typical nominal temperature. Again, it depends on the thermal properties of your jacket. How well does it insulate from the outside temperatures, things of that nature. You can get a little higher range if you're trying to do indirect contact with skin, if you're embedding these types of heaters in garments. And you can go even higher than that if need be, if you're trying to heat through foam, neoprene, different types of fabrics whatsoever.
We've got a couple of questions here, Mike.
Yes.
I could stop for a moment. The first one I believe I can answer. Ron asked a question, does Butler Tech handle the design of the heating elements? Yes, we do the design in-house. He was also asking about control circuits. Do we handle the control circuit design?
We do not, but we can outsource that if you need help with that. Okay. If you're more of a garment manufacturer and you need help with the heater and the control system, that's something we can do. We contract part of that out because we don't make circuit boards and things like that, or an enclosure, items that might be made into a control module.
Thanks. And then we have another question from Ed. He asked, what's the lowest equilibrium temperature and highest power density that can be formulated for a PTC heater?
So for the wearables, typically you can go between 0.2 and 0.3 is very typical for wearables. We don't typically deviate above that for wearables, but you can go higher than if you're doing more industrial, 5, 10, 15, 20.
Yeah, his second part of that question is, can it be applied for snow melting applications requiring high power density but low temperature?
Typically, you'd either have to go into a polyester version or onto a Kapton material to do that. Because you can get these things pretty warm, right? But you don't want to, if you're putting on TPU, you're going to damage the TPU.
Okay. So
typically in applications like that, you're using a different type of heater, not necessarily designed for wearables, but similar technologies involved, and you can do that.
Okay, thanks.
And then, so if you're going to do higher temperatures, for example, when you have unique materials that you want to work with, as far as like textiles, for example, we're probably going to do some R&D with that particular textile, just because we've not worked with every fabric in the world. So usually there's an R&D type or a prototype order, and we work through that with a couple of iterations to dial in the heat that you need for your particular application. So again, in industrial applications, again, really not what we're talking about today, but I wanted to cover that because you can still use wearable like TPU and PET for some of these applications. Again, are you heating a space like indirect heat, almost like the cabin of an aircraft, or for example, the car, or direct heat? Are you heating an item? Are heat sink or thermal drain considerations? And then thermal modeling may be required. And that's a source that we don't really do inside. We would outsource that. So let's talk about heater size. So this is where people get a little hung up sometimes, because they think I only have a space for a 4x6 heater, but it has to get a little bit bigger than that because you have different elements of the heater to heat that particular area. So there's a heating zone versus the actual heater size. The overall heater size is larger than the heating zone, and you can see that kind of in the diagram. We'll go through that. So this needs to be considered in your design. So let's talk about the primary components. In the image, you'll see the bus bar area outlined in green. So that adds some thickness. Those might be a 1/4 inch or a 1/2 inch. wide. And so that adds at least an extra inch itself to the length of the heater. So instead of being 6 inches, now it's 7 inches, for example. So just things you need to consider. Bus bars are important, the thickness of those, because you don't want a voltage drop. Like in this design, from where you're hooking up the power to the terminals, you want a minimal voltage drop because you don't want the furthest away heating elements to see a voltage drop. It's going to make the heater very uneven. Let's talk about power requirements. So we should know what your voltage supply wants to be. What's your power density target? Again, it's kind of scalable. Once you dial that in, you can go from a smaller heater to a larger if you know what you want. And again, for the wearables we work around, it's about 0.2 to 0.3 typically watts per square inch. Battery size, again, we get a lot of questions on that. So once we know what battery size you're going to use, we figure out maybe what's going to be the current draw that heater will have, and that'll determine the length of time that you can heat with that battery. And so battery sizes are usually in milliamp hours. So if I had a heater basically that drew 500 milliamps of current, and I had a 5,000 milliamp battery, the heater would stay warm for about 10 hours before needing to recharge the battery. So just some examples. Connection types, this is probably the most tricky from the standpoint of what we can do and what you might want to do in integrating the garment into or the heater into your garment. Things that we deal with, snaps like garment snaps. You can see there's a snap on this picture that is going to snap to basically a common electrode snap used in medical applications. They have magnetic versions of that too. We've done some compression fit type connections where basically there's a conductive pad maybe on a board embedded into a waterproof housing that actually compression fits to the heater terminal itself. We've done things with conductive epoxy, crimped solder pins to our heaters, and then wires would be soldered to that and then waterproofed. And then direct wires as well, whether that's riveted into the heater or soldered on our end to the solder pins or solder tabs. Again, that's a minimal thing, but it needs to be discussed because that's usually the last thing people think about. And so, Jamie, you want to take over here?
Yeah, so I just wanted to kind of wrap up and then we can take questions. We wanted to also announce that one of the things that we're doing now, we're taking pre-orders for development kits for prototyping. So our team's been working on these things. Do you have the text there you can pop up, Mike? So we have two different types in each kit. So a kit will get you 2 of the PTC heaters pre-mounted to fabric and 2 fixed resistance heaters pre-mounted to fabric, along with snap connection, power cables, and a 12-volt battery. And so the idea behind this is we want to be able to help people get to market faster. We have a lot of people that come in and they have an specific application, or maybe they're trying to, whether it's go for funding or make a pitch towards a customer. And rather than going through the process of trying to design a custom one just for that early stage, we've developed these kits to help get you to market faster. So they are now going to be available on our website. If you go to butlertechnologieshop.com, you can see those and actually pre-order them. I have an example of one of them here in my hand. So this is the size of it. That's what you've been seeing pictures of. So these things are already pre-mounted to fabric that you can take and put into your application for whatever type of testing you want to do, or to be able to do a demonstration for your customers.
And typically you're going to sew those into the fabric of your garment.
Correct.
And
yeah, they come with the data sheets and everything that you need to do, everything you need to know to get going. And then on the other side of it too, if you do get to the point where you want to develop something for a specific application, you can reach out to any one of us here at Butler Tech and we'd be happy to help walk you through it. So on our end, again, this is our sales team, our printed electronics. You've got myself, Mike, and Todd Gray on the line. If you have questions, please reach out to us. Again, we'd be happy to help you. We're going to open this up to questions, but the one thing I wanted to mention before we do that is this webinar series, we're going to be starting these up where there's going to be multiples throughout the year. Our next one is going to be planned for March. We're going to be working with Chasm Advanced Materials to talk about clear, transparent heaters for automotive applications. So if you're interested in taking it from wearables into an automotive, join us in March. Check out our social channels where we're going to be announcing when that webinar is. So now I'll turn it over for questions. If you guys would like to come off mute and ask questions, you're more than welcome. Oh, so Ron also asked, I just saw this on here, for a PTC heater, is only one temperature achievable?
So there's a couple different ways to answer that. There's multiple temperatures achievable. Let's say you have one specific ink that you're using, it has a max temperature. You can then drop the voltage input to change that temperature. So if you want multiple heat settings within the same heater, you can do that, but it's only going to reach a maximum temperature. So if you need that to change that temperature range, you're going to go to a different PTC ink, and there's multiple PTC inks on the market that have different shut-off temperatures, we'll call it.
Yeah, so we just got a question here. Can you comment on inks, performance and aspects of the inks today that can use improvements, and why that would help a wider rollout of wearable heaters? So just basically talking about the inks that are on the market today and where can we use improvements?
Yeah, the first thing is, the stretchability of the inks. Making sure that your company, if you're an ink manufacturer, you can produce these types of things, because, we've printed wearables way back. I mean, going back more than 10 years ago on TPU, but the TPU stretch and we can bond it, but the inks just didn't adhere well to the TPU. And if they did not stretch, they cracked. So basically then the heater failed. So that's been the kind of the first advancement in these wearables, is people making inks that can stretch fairly well, and then finding compatible materials, the TPUs or whatever you can print, or even let's say TPU or vinyl or polyester coated fabrics, something like a company like Easttech, you can print directly onto the coating on the fabric itself. It's almost like a TPU film bonded to a fabric, and you print directly onto that. But yeah, I would say the flexibility, the stretchability is huge. And then obviously the washability is the other issue. And if you talk about, let's say you're going to go into biosensors as a different wearable, the wear factor for the electrodes is very big. You want to make sure you can get obviously good signal from the skin, and there's a lot of different tricks you can do for that. And we've developed some of our own proprietary tricks, so to speak. But you have to make sure that they don't wear out quickly, especially if you're doing a type of athletic garment where there's a lot of movement on the skin, sweat, things of that nature. And then the PTC inks we found sometimes are, if they're a wearable version, they can be a little bit volatile as far as how well they last from a shelf life standpoint. Once they're in their, their liquid state or their paste state, how well they are stable, how long they're stable, if they're exposed to ambient temperatures or when they're shipped, things of that nature, and how stable and how mixed they stay. We constantly rotate our inks on a roller system, so they're constantly moving. They never stop once they get in our facility. And that keeps them mixed very well. Otherwise, they tend to change properties a bit, and it's very hard to get them back to where they should be. Kind of covering some things we've come across.
Okay, I've got a couple more questions. I also wanted to let the group know that I guess I had unmute unavailable, and so I just corrected that if you wanted to jump on. But I've got two questions here. What's the service life of the material given temps not exceeding 122 degrees Fahrenheit?
Typically your inks are going to fail probably prior to that. So again, you could get years out of this, for example, but it depends on how much you're washing it. So if you're going to 100 washes, it's not going to last, you're going to be coming to the end of life, depending on whether you're machine washing that, or if you're going to hand wash it, which is what I would recommend for a jacket. Just also keep the integrity of a jacket, for example. But I mean, we have our Olympic jacket that we did the heaters for, and we have a version of that, and that's going on, what, 3 years now?
Mm-hmm.
So, I mean, it's still viable. It just depends on how much you use that. The bigger things we've seen sometimes when you wear it or wash it in excessive amounts, you have to be more considerate of the heater itself debonding from the fabric a little bit at the edges. I've seen that happen from excessive washing or harsh washing.
Okay.
But again, we're shooting again for these wearables. If you're going to wash them, 25 to 50. In some applications, maybe if you're gentle hand washing, you can go up to 100.
Thanks. Another question regarding cost, and this says, can you give a rough estimate ballpark of cost versus other types of heating tech?
That's a difficult one, and cost always is, but it's because so if you want to just compare like a $20 etched heater that's used maybe for industrial, if I want to do a printed wearables one, that could be $20 to $50, depending on volume, right, or size.
Okay.
We've had them down to $5 or $10 in great volume, so it's not so bad. But it just depends. It's like anything else. It depends on volume, because we can get better price breaks on the inks and the substrates as well at higher volumes.
Okay. Are there any other questions? I think that's it. Well, we got a couple of them coming in. Another one. Is it possible for dual phase PTC formulation for the first for temperature regulation, the second for a sacrificial fuse preventing NTC?
That's a good question. Since we're not an ink manufacturer, I don't know if you can build something like that. You might be able to print it if we can find the right inks. I know what you're talking about.
Interesting.
Yeah, I mean,
Okay.
You can build a fuse. If you put enough current through it, you'll burn out, let's say, a resistive element. Something like that. We've actually printed fuses before, not for a wearable application. It was industrial. But it had to get pretty hot in that area to burn out the ink and the substrate. So I don't know if you want to get that little hot spot on a wearable.
Right. Okay. Well, if there isn't any other questions, I just wanted to thank everybody for joining us this afternoon. We appreciate your time. And again, if you have any questions, reach out to Mike or myself or Todd Gray. And thanks again for joining us. We really appreciate it.